Okay, so to start off today, we do have two videos that we'll go through, so we'll start the session with those.
In January 2020, a specialist contractor was engaged to upgrade the drift winder at a New South Wales coal mine. The contractor was required to remove the drift winder rope and developed its own procedure for the project. The winder rope was to be fed from the mine's drift winder through the existing head sheave to a mobile friction winch and then onto a rope reeler. The contractor undertook the rope removal during a planned shutdown on the 6th of October 2020. The task was performed by a work crew of 5 contractor workers and a mine worker. At around 12 p.m, crew members erected barricading taping to demarcate and restrict access to the work area. The crew believed they had approval to enter the work area. At around 12:45 p.m, some of the crew participated in a task analysis, which reviewed each step of the rope removal procedure, identifying relevant hazards and agreed controls to ensure it could be done safely. The task analysis identified equipment failure caused by over-tensioning as a hazard. Maintaining visual slack in the rope, radio communication, maintaining line of sight, and taping off restricted areas to keep workers out of the line of fire were the agreed controls. At around 4 p.m, the crew began removing the rope from the drift winder. This required simultaneous operation of the involved plant and coordination using UHF radio, direct line of sight, and hand signals to ensure sufficient slack was maintained. Tension in the winder rope increased, introducing significant force on the head sheave assembly. At around 5:53 p.m, the head sheave assembly failed and the 3-ton head sheave dislodged and fell 14 meters to the ground below. At the time, a crew member was on the ground directly below the head sheave tower within a taped-off restricted area. The worker had to evade the falling head sheave, moving clear moments before it hit the ground. No one was injured. The incident was reported to the New South Wales Resources Regulator, who investigated its cause and circumstances. The investigation found the primary cause of the incident was over-tensioning of the rope between the drift winder, friction winch, and head sheave caused the structural failure of the head sheave bearing assembly and hold-down bolts, which in turn dislodged the head sheave, causing it to fall. The over-tensioning most likely occurred when the drift winder stopped unwinding while the friction winch and rope reeler continued to wind in the rope. Prior to the incident, a third-party engineering report was obtained, assessing the structural integrity of the head sheave tower and assembly. The report assessed a proposed 12-ton rope load based on the methodology drawing provided by the contractor. It found the head sheave shaft and hold-down bolts were non-compliant with relevant Australian standards and recommended an 8-ton rope load limit and that the hold-down bolts be replaced. The incident investigation determined the following key contributing factors. The project's overarching risk assessment failed to appropriately identify and assess the relevant risks and controls associated with the rope removal. The third-party engineering report's recommendations had not been appropriately addressed by the contractor. The friction winch was capable of exerting line pull forces on the head sheave assembly in excess of 4 times the 8-ton limit recommended by the third-party engineering report. The rope removal methodology lacked engineering controls to prevent the rope becoming over-tensioned, had no method of obtaining information in real time of the actual line pull forces being exerted, and had no method of remote task observation, such as cameras, eliminating the need for workers to be positioned within hazardous areas. The rope removal procedure did not incorporate higher-order controls, such as hard barricading, to create a physical barrier to hazardous areas in the potential drop zone of falling objects. The rope removal safe work method statement, procedure, and task analysis did not clearly define the locations, classification, and entry requirements for the barrier-taped areas during each specific job step. As a result, the workers were operating within hazardous areas on the premise that these areas were control zones which they had been granted approval to enter. It is recommended that persons conducting business undertakings who are involved in driftwinder construction, operation, and maintenance works ensure driftwinder rope removal procedures eliminate, where reasonably practicable, or otherwise minimize the risks associated with rope overtension by using fit-for-purpose plants suitably powered and configured for the task, higher-order engineering controls such as load cells and interlocks preventing the exceedance of plant-safe working load limits, higher-order controls such as hard barricading to create a physical barrier to hazardous areas in the potential drop zone of falling objects, and remote monitoring devices such as cameras to eliminate the need for workers to be in hazardous areas. Ensure documented procedures clearly articulate exclusion and restricted access areas with clear instruction and guidance provided on the locations, classification, entry and exit requirements. And ensure workers have appropriate training and instruction in procedures and risk assessments so that requirements are clearly understood and adhered to. It is recommended that workers comply with implemented hazard identification and risk management processes to ensure that when conditions or procedures change, adequate new risk control measures are put in place. Always maintain situational awareness and never enter areas in the potential line of fire of falling objects. For more information and to see the full report, visit our website.
So that incident you saw just there, we were supposed to undertake obviously 2 roping activities as part of that job. We were to do the rope removal, then we'll do a winder installation, and then we do a rope installation later on. During that rope removal, we don't need any tension between the winder and the friction winch. We only need storage tension on the reel between the friction winch and the reel itself. So we only need tension there, just enough to store it and prevent any damage during the storage of that. Hence why there was not a lot of engineering higher rated controls around the slack rope monitoring. As long as we had slack there and we had a loop there, that's what we needed for that part of the process. However, the engineering controls were actually in the system. When we do the rope installation piece, we need it under tension to do that. So we've actually got to store 50% of the working tension into the drum. So there was more focus at the time put on that part of the activity, being the higher risk, than there was on that rope removal process. So I'll just play the second video.
In October of 2020, SIEMAG TECBERG Australia began the on-site installation portion of a driftwinder upgrade project at a colliery in New South Wales. During the removal of the winder rope from the driftwinder, the head sheave was dislodged from its support frame due to excessive tension on the rope and fell approximately 13 metres to the ground below. Following the incident, SIEMAG TECBERG, formerly known as Winder Controls, made a number of changes within the business. The primary change was a management restructure to ensure that roles and responsibilities of each manager were better aligned with the requirements of their departments. SIEMAG TECBERG also implemented a company-wide action tracking system, which enables employees to more accurately manage tasks and to ensure that actions that come out of meetings and risk assessments are followed through. This also allowed the management team to have easy access to an overview of tasks and their status at any given time. SIEMAG TECBERG went on to successfully complete the installation of the winder in January 2021 and developed a new rope installation procedure using lessons learned from the incident. Additional load cells were implemented to monitor the rope tension. These consisted of inline load cells to monitor T1 and T2 tension on either side of the friction winch, and a sheave load cell to monitor the load on the sheave. All load cells were interlocked to the operation of the equipment in order to prevent excessive tension in the rope. CCTV cameras were installed to monitor key items of equipment which were previously being monitored by spotters. These fed to a control centre within the winder room and eliminated the requirement for personnel to be positioned in high-risk areas. 2 barricaded areas were erected around the rope installation area. The first, larger area was erected to restrict access to the area to only those personnel who were required for the installation tasks. The second, smaller area was erected as a no-go zone for all personnel while the reeler, friction winch or winder were operating. No one was allowed into this area at any times during operation. Noise-cancelling radios were provided to all relevant rope installation personnel. Rope removal was carried out by a team of 6 individuals from SIEMAG TECBERG. The winder driver, friction winch operator and reeler operator monitored the equipment using the CCTV displays and compared the load readings from the load cells and equipment readouts during the rope installation. A spotter was positioned on the tower to look down onto the friction winch and reeler, and also to look along the length of the rope going into the winder drum. A second spotter was positioned alongside the no-go zone, looking at the inline load cells and the rope going through the friction winch. A third spotter was positioned some distance from the installation area, monitoring the rope slack between the sheave and the winder. The rope installation began by using an air winch and fibre rope positioned behind the winder to pull the end of the winder rope from the hydraulic reeler through the friction winch and around the sheave back towards the winder drum. Once the rope had reached the winder drum, the friction winch, air winch and hydraulic reeler were isolated and the winder rope was secured at the winder house window to an approved anchor point with poly rope clamps. The rope was then fed through the horse hole and into the rope anchor clamps. The inline load cells were then installed on the T1 and T2 sides of the friction winch. The hydraulic reeler was set to maintain a nominal tension on the back of the friction winch at T2. The friction winch and winder were then used to slowly apply a load to the rope, while the rope tensions were compared between the load cells, friction winch and winder readouts to ensure that all items of equipment were reading as expected. When the rope end reached the head sheave, the friction winch, hydraulic reeler and winder were isolated. The air winch, which was used earlier in the installation, was then moved to the flat top on the drift in order to pull the rope to the dolly car for rope attachment. The rope installation was completed successfully on the 15th of January 2021, and SIEMAG TECBERG Australia went on to complete commissioning of the drift winder in February 2021. SIEMAG TECBERG Australia has developed a rope handling informative to serve as a checklist for the industry to reduce the likelihood of future incidents occurring. This tool is designed to support the responsible person's decision by allowing them the confidence to proceed with the task or project or stop the task or project, knowing that too many questions are unanswered.
Okay, so just a little bit about SIEMAG TECBERG. So SIEMAG TECBERG has a global presence all over the world with most mining markets. So we've been in the hoisting business since about 1871. Our headquarters are in Haiger, Germany, with over 400 employees globally. So in Sydney, we have a head office in Australia, and then we also have an office in Newcastle. So the key strength of SIEMAG TECBERG's business model is to leave full flexibility and free choice with the client. So one of the few companies in the world that can supply all types of winders. Our drives of all leading suppliers can be integrated into our systems, and the use of in-house or third-party automation solutions are possible. So prior to the actual incident, we conducted a construction risk assessment. So the risk assessment included the rope handling activity. We reviewed the existing procedure to carry out the rope removal. We reviewed the engineering design report to understand the design capacity of the sheave and the tower in conjunction with the rope removal procedure. We familiarised the rope removal team with regard to the procedure's contents. We carried out factory acceptance testing of our rope handling equipment because that's what we do as a business. So we supply the rope handling equipment to do these installations, so the friction winches, the reelers, all those winches, that's what we do as a business. So we often set those up in the workshops for that specific task once we know what the rope handling activity is, what the loads are, and then we deliver those to site, and we set up the site barricading zones to prevent personnel from entering the high-risk areas. And we set up communication equipment for the nominated personnel to control the task. Now, obviously, on the day we got it wrong, and so post-incident, we did our own internal reviews, and we installed the new rope sheave that was planned to happen later on, which gave us the extra capacity in that tower and gave us live monitoring underneath that sheave. So we commissioned that load cell for the final windage system underneath the deflection sheave. We installed secondary inline load cells to monitor rope tension. We changed the readout screens on the friction winch from motor percentage to line pull. So that was a big one as well. We increased the barricading zone. We installed CCTV monitoring systems, so we didn't have to have people as close to the winch rope for the removal or the installation, and it also gave the operators of the winders and the winches better picture and understanding of what's happening around the area. We also installed set point monitoring to measure motor current to limit the capacity of the winder. And then, so obviously after the event, SIEMAG TECBERG Australia entered into an enforceable undertaking with the New South Wales Resource Regulator. So SDA proposed 4 projects which would deliver benefits to workers, industry and the community. So that was the rope handling informative, which is what we're going through today, the incident animations and the presentations that we also have gone through today, mental health awareness training modules, an induction pilot and supporting the Mates in Mining course, and then an opal mining shaft safety video. So back into the planning, and as we begin the rope handling informative, I'll bring us back to the hierarchy of controls. So as engineers, we're typically engaged to find solutions when elimination or substitution is not possible. So whether through site engineers or partnerships with companies like ourselves, that's typically often where we'll find the best next level adequate controls for a project. So engineering controls we design are to address the hazard at its source, and they're to eliminate, minimise or control the risk to as low as reasonably practical. So through the use of adequately designed and installed equipment, well maintained to prevent erosion of the hazard controls, these can be long-term effective solutions. So when planning the task, we need to consider the use of engineering controls reasonably available to complete the job safely and effectively. So line pull when doing rope handling tasks. The use of line pull monitoring is an essential step to be considered. Line pull can be monitored using inline load cells attached directly to the ends of the wire rope. You can use strain gauges, so they're bonded to the actual wire rope, and they're used to measure change in length of the rope to then tell you how much strain is in that. Tension meters, they're similar to inline load cells, however they're clamped to the side of the rope where you bend it, and you can measure how much tension and rigidity is in that rope. Load indicators, you often get them attached to the rope end or the rigging itself. So the use of line pull monitoring can be used to limit and ensure the equipment is appropriately sized for the task. So limiting the torque output or energy consumption by the equipment and making use of continuous monitoring that trip the equipment in the event of maximum limits are reached. Because as I said before, we supply friction winches designed to do many jobs. So we have that friction winch, for example, that blue one has a 60-tonne capacity. So we would limit that for the task we need to do. And then we'll set those limits with the line pull monitoring to actually make sure that we don't exceed those. So the other factors that we need to consider are the structural limitations on the equipment we're working with. Because often we'll go to site and we're either doing modifications to the existing gear, or we're removing and installing new. But we just need to make sure that we have understood all loads imposed through that task and make sure that we're not going to exceed any of the capacities. So head frames, structures, they're critical in determining the tensions and loads to be induced. So it's essential during rope handling when you're potentially changing the normal operating conditions of the plant and equipment, because we are now introducing new loads that type of equipment don't normally see in potentially new directions. We use deflection sheaves a lot when doing our rope handling activities. So deflection sheaves, they're pulleys or a set of pulleys that are used in rope systems to change the direction of the rope and control the angle of pull. So these are designed to reduce the amount of stress and wear on the rope by spreading the load over multiple strands and distribute stress evenly. So they're commonly used piece of equipment, but if used incorrectly or sized incorrectly, they can pose a significant risk. So the use of deflection sheaves with steel wire rope involves the following risks. So overloading the sheave or the structure which it's mounted, this can cause the sheave or the structure to fail, leading to the loss of load or potential injury to personnel. Misalignment can cause increased wear on the rope sheave or the rope, reducing the rope or the sheave's life and leading to potential failure. Rust and corrosion is something that we always have to deal with, especially with sheaves and storing of equipment or equipment that's exposed to the atmosphere outside. Improper maintenance or inspections can result in sheave failure or identification of a potential that could cause failure. So to minimise these risks, it's important that we regularly inspect and maintain the deflection sheaves, that we ensure that we've got proper sizing and alignment of loading, and we follow the safe operating procedures to ensure that safe and efficient use of those sheaves. Another factor that you need to consider when doing rope handling activities are fleet angles. So fleet angle is the angle between the wire rope and the centre line of the drum or the sheave. So as you can see in the picture, you've got to account for the extremes. Now when going to a single strand sheave, it's pretty straightforward. From the worst cases are obviously the ends to that sheave, or the centre point also is not an ideal condition back to the sheave. But if you've got two winches and drums, then you need to make sure that you're also factoring in the diagonals. So excessive fleet angle greater than the design capacity of the sheave, the drum or the rope can rapidly deteriorate the rope, leading to reduced life of the rope, sheave or the drum, and potentially lead to catastrophic failure. So fleet angle is an important factor to consider when installing steel wire rope onto the drum or removing rope from a drum for the following reasons. So as mentioned before, the fleet angle affects the amount of wear on the rope, because incorrect fleet angles can cause excessive wear, especially back in these points around here and then here, but then also as the rope is going from one layer to the next and binding over and rubbing on itself. The fleet angle affects the coiling of the rope onto the drum. So incorrect fleet angles can cause the rope to miscoil and or lead to potentially damaging the rope. Incorrect or excessive fleet angles can cause reducing the load capacity of the rope. And in in the past, in history, that has actually led to rope failures completely. Fleet angle affects the stability of the rope as it trucks onto the drum. So incorrect fleet angles can cause the rope to slip, also leading to damage or potential injury. So it's important to follow the manufacturer's recommendation for fleet angles for the specific equipment being used, because there are different limitations for fleet angles depending on the equipment. For example, winders, we have the 1.5% fleet angle limit, but then you've got winches have higher limits at 3%, and then you've got cranes have different fleet angles in their design as well. So it depends on what type of equipment and what standard you're designing your equipment to, and what the equivalent limitations for the fleet angle. But you also need to factor in your rope construction, because depending on your rope style, they also may have a higher or lower fleet angle tolerance. So I mentioned before about the 50% nominal tension. So it's in the TRG that there is a requirement to have 50% nominal tension on the actual dead turns of a drum. And in particular, the reason, primary reasons behind the guide is the dead turns, they're not used in service. So therefore, pre-tensioning must be installed into the rope to prevent the subsequent layers actually pulling into the bottom layer, causing damage. Secondary reasons, so you need to preload the rope so it gets to its actual operating diameter from its relaxed diameter, to make sure that when it's at its operating diameter, it is bunched up and all tightened, and so there's no actual potential air gaps in the future. And it's also there to prevent any slip between the rope and the drum, because if they are loose there on the dead turns as you're putting subsequent layers on there, you can get it actually grinding away on the rope and the drum itself. We always need to consider layout. So the layout of the drums, sheaves or newly introduced equipment, and the items that need to be reviewed are consideration of changing the rope sheave to one that is better suited. For example, a rope sheave with a different diameter, a different groove shape or other characteristics. Consider adjusting the position of the drum or the sheave to better achieve correct fleet angle. So you can either get the two further away from each other, or if you had to, you can actually get another sheave in line to create a different distance to then also achieve your fleet angle. So that's the consideration, the possible introduction of an idler sheave into the system. So these can be installed to guide the rope and help achieve the correct fleet angle. So for new or upgraded systems, we also can consider the rope type that can handle higher fleet angles. So it's important to work with experienced engineers or rope specialists to determine the best solution for the given application, because in some cases it may not be possible to achieve the correct fleet angle, and other solutions such as the use of a different type of rope or a different type of rope handling equipment may need to be considered. The safety and reliability of the rope handling system must always be the primary consideration when making any changes or modifications. Again, any rope handling activity, you need to make sure you have adequate exclusion zones. So identifying exclusion zones in the planning stage and implementing controls to minimise the need to enter these areas are essential in reducing exposure to our employees and our contractors. Adequately identifying and demarcating the difference between controlled zones and exclusion zones to minimise any doubt or confusion to our employees or contractors. Exclusion zones are typically established for areas where there's hazardous activities being conducted, dangerous machinery operating, equipment or materials are stored, maintenance or repair work is being performed, or emergency situations have arisen. So designing exclusion zones must consider the following. So identify the hazard that has the potential to actually cause the harm. So assess the risk of that hazard becoming an event or causing harm to our employees or our contractors. Ensure that the exclusion zone is large enough to allow safe operation and maintenance of the equipment, and consider all possible entry points from personnel outside the working group. Establish clear boundaries and consider all possible entry points from personnel working outside the group. Implement measures to control access, such as gates, locks, or if you have to, security personnel. Provide training to personnel on the purpose and the use of exclusion zones, and ensure that they understand the risks when entering the zone. And then you need to regularly review and update exclusion zone design and procedures as needed. So once we set our plan, things change. You always need to go and re-review and make sure that plan is still adequate. So the use of CCTV. So again, we need to challenge ourselves. Do you really need to be there in person to actually have a look at the equipment? As rope handling companies, they often like to be there to listen to the rope, to see the rope, and get a good understanding of what's going on. So again, just challenge whether or not you really need to be in that area. Because with today's technology and the clarity of CCTV systems, they're a great tool to set up instead of using spotters and waiting on delayed communication in the event of change that could pose a risk. There are cameras for almost all situations, whether it's either difficult or could pose a risk to personnel being placed in that location as a spotter. Using CCTV cameras and personnel can monitor what is happening in multiple locations over large areas from a safe location. With any task, it's critical that we document all the good work that we've undertaken to assess all the risks for an efficient and safe outcome. So once the scope is understood, this all starts with that risk assessment, with the basic methodology known and the adequately skilled personnel involved in that risk assessment. That drives the procedural review, the job planning, equipment procurement, personnel planning, emergency response, inspection records, your permits. That all just underpins from that risk assessment and job planning. Remember, our permits are a great tool as the reminders of the people on the job. So they're there to make sure that we are checking everything we need to check. Our personnel on the job don't forget. That permit is there to be that reminder. Our labour. So training, necessary training and qualifications to perform the task. We need to make sure that we have the right qualified people, that they have undergone training, that it's frequent training and often refreshed. Presentation before was a great example of supervisor training. We also need to make sure that our workers are continuously undergoing that style of training and not just rely on something that they've done years ago, because things change, experiences change. We often find new ways of doing things or safer ways. So we just need to make sure that we provide that ongoing training and support of our personnel. So when choosing personnel to perform a potentially hazardous task, especially on mine sites, a number of factors should be considered to ensure the safety of our workers and a successful task. So some of these considerations are their experience, their physical abilities, their record, their availability. Availability can become a big one, especially when you're calling contract companies in and there's multiple things going on. So we just need to make sure everyone is set, calm, and got their head in the right workspace to attend site and carry out that task efficiently. And then that they can communicate adequately as well. So communication, it needs to be effective. So some suitable means of communicating are face-to-face, two-way radios, hand signals, written instructions, signage, by using a combination of these communication methods, mine operators can ensure that workers have the information they need to perform the task safely and effectively. But we need to also make sure that they understand what you're trying to say. Sometimes we aren't clear in our communication methods, so we need to make sure that the people we're communicating to understand what we're trying to say and provide that feedback to us. Because there's been countless incidents in the past where you might have thought that you've communicated adequately, and then you find out that they've interpreted it completely differently. So on the regulator's website, SIEMAG TECBERG Australia have developed a checklist to be used as a guide for all future companies, contractors or mine engineers to ensure that all possible aspects are considered when performing rope removal or rope installation on mine winders, winches or any rope handling task. So this checklist is there. It's very broad and it's available for anyone to go through. And again, it's supposed to just be that brainstorming when planning jobs. When actually on the jobs, use that as that check to go through and make sure that you can do that job safely. And that's all I had for today. Thank you.